Okay, so here's a recap of the two theorems that we want to prove. So theorem 1 says that for every G there exists a self-shrinker with genus G, which is non-compact, complete, embedded. And theorem 2 says when we let the genus G go to infinity, then these self-shrinkers converge to the intersection of the plane and the sphere of radius 2. Okay, so how do we prove theorem 1? We use this black box called min-max theory, okay? And just to give you a little bit of an idea of how this min-max theory works, in case you're not familiar with this, let me illustrate two examples. So min-max is used if you cannot use a minimization approach or gradient flow approach because you want to find a saddle point. So imagine you start somewhere up here and you want to minimize, and if you're super lucky you might get to that saddle point, but what is much more likely is that you somehow drift off here and you miss the saddle point and you will never find it. So for this reason, to find a saddle point instead of finding minima or maxima, you use this min-max approach, okay? So if we have any curve that goes from a low point here to a low point there, then this curve will reach at least the height of this saddle point. So that's an important condition, so we will call this the mountain pass condition, which means every curve that goes above this saddle at some point is strictly larger than these two low points in these valleys, okay? So in particular there's a maximum that is much higher, okay? And then what we can do is we can look at the infimum of all these maxima. So we always take the maximum, the highest point, and then we minimize over all these maxima, or take an infimum over all the curves, and then the hope is that these maximum points will converge to the saddle point, and the height will converge to the height of this saddle, okay? So that's why it's called min-max, because you take the maximum within every curve and then you minimize over all the curves. And that's a way to find saddle points or unstable objects, okay? So how is this applied in a more geometric setting? So if you want to find, for example, a closed geodesic on this ellipsoid, so let's start with some curve. Then if we shorten that curve, for example, by curve shortening flow or Birkhoff's curve shortening process or some other method, what might happen is that this curve might just move up and somehow disappear, and you will not find any closed geodesic. Okay, so in order to find a closed geodesic, that's the same thing as we didn't just start with a point here and let this point evolve, but we actually looked at a family of curves. So in this case, we look at a family of closed curves, which is called a sweep out. So you start at a point, you end at the point, and in between the length gets longer and longer, okay? And now what we'll do is we look at the longest length and see whether this longest length is already pretty good. And then we look at similar other sweep outs, so sweep outs that sort of are in the same isotopy class as this green model sweep out. And they might be much better, so the red one is a bit better because the longest curve in the red one is shorter than the longest curve in the green one. And then the blue one is even better, okay? And now if we only focus on these longest curves, the hope is that these will converge in some sense to this sort of equatorial closed geodesic, okay? And the same thing happens for minimal surfaces. So the min-max construction we use is that. And what we want to create a minimal surface in Gaussian space. So we want to create a two-dimensional surface so we look at the whole family, a whole sweep out of two-dimensional surfaces of our three-dimensional Gaussian space. And how do we do that? So we do this in an equivariant way, because that means we want to keep some symmetry, and the symmetry is the symmetry of the self-shrinker that we want to find. Okay, so here is a picture for genus equals 3. So in genus equals 3, the symmetry group should be the dihedral group dg plus 1, and then g plus 1 is 4, and here we have 2 times g plus 1 is 8 such sections in which we divide the plane, and then we also have this circle of radius 2, and then we color this way. Okay, so for higher genus, always we have outer regions 2 times g plus 1 and 2 times g plus 1 inner regions, and we cover them this way. And then we glue the dark regions to an upper hemisphere and the light regions to a lower hemisphere, and then we this way we obtain a surface sigma, but that's not yet smooth, so we slightly smoothen the edges that we have created this way. Okay, and that is our model sigma. But that's so far just one surface, it's not yet a sweep out, but it's very easy to get a sweep out. We just scale it. So we let sigma t be t over 1 minus t times sigma. So that means if t is 0, then that sphere has been shrunk to a point, and then if t becomes larger, then the sphere factor becomes larger, and then it blows up when t goes to 1, the sphere goes all the way to infinity, and we are left with a plane again. Okay, so in particular this gives us a sweep out of R3. Whether it's with the Gaussian metric or not, that's not important for the moment. Just we sweep out the entire space, and we have the right symmetry, and we have the right topology. Okay, we have the topology that we want for our self-shrinkers, we have the symmetry that we want for our self-shrinkers. Then we also know that sigma at 0 and sigma at 1, so that corresponds to these points here where we started, and in between we have these longer lengths. So here we are working with Gaussian area. The Gaussian area of sigma 0 and of sigma 1 is 1 because it's just a plane. Okay, and then in between, the Gaussian area for this model sweep out never goes above the area of the plane plus the area of the sphere. Okay, remember the spheres had actually the largest area at radius 2, which was 4 over E, and then if the sphere is smaller or if the sphere is larger, then the Gaussian area is smaller than that. What is important for us is that this number is less than 3. Okay, so it's about 2.47 or something, and even if our smoothing, actually it can be done without losing this property. The smoothing actually improves the area bound, but even if we smooth in a more complicated way, as long as we stay below 3, everything works. Okay, good. Now we saturate. So saturating means we don't just look at this model sweep out, but we look at the whole family of sweep outs. So we have this family. So we have this sweep out sigma t, and we evolve this or we change this with some isotopy, and the isotopy should be dg plus 1 equivariant, so it preserves the symmetry. Okay, so we modify our sweep outs, we saturate our sweep outs, and we only look at the ones that have the right symmetry and topology. And then we define this width, and the width again is we take the supremum of, or the maximum of the Gaussian area, and then we take the minimum or the infimum, over all these elements in this saturation. Okay? Good. Now, in order for this min-max black box to actually work and give us something, what we need is this mountain pass condition. So we need to know that this width is always going to be strictly bigger than 1. So we need to go at least at a certain height, say 1 plus delta. Otherwise, we cannot conclude that there is actually this mountain pass point. Okay? So how can we conclude that? So this is using the stability of the Gaussian isoperimetric inequality. So what is that? So the Gaussian isoperimetric inequality says in Gaussian space, the regions that have the least perimeter are the half spaces, okay, or the best. Let's say if they have half the volume of the entire space and least perimeter, then they're half spaces. Okay. Now we can also do this in an equivariant way. If they're additionally having this dg+1 symmetry, then they need to be equivariant half spaces. There's actually very few of them. So there's the upper half space, the lower half space, and if the genus is very low, then there's maybe some other half space. But for high genus, there's only the upper and lower one. Okay? Good. So now how do we get this width estimate from that? So there's this stability result which says minimizers for this Gaussian isoperimetric inequality are half spaces. But if you're close to the minimizer, that in the sense that you have half of the volume of the entire three-dimensional space, and you have perimeter less than 1 plus delta, then you must be close to a half space. Okay? So now assume that this width estimate would not hold. So that would mean along one of these objects in this saturation, so one of these sweep outs, we can go from the sigma 0 to the sigma 1, or what corresponds to sigma 0 or sigma 1, without ever having Gaussian area larger than 1 plus delta. So always staying below 1 plus delta. But that means along the entire sweep out, we're always close to a half space. Okay? Or let's say, pick one of the two half spaces that is bounded by this figure, by our sweep out, and then this one always stays close to an actual half space. And because of the equivariant condition, because there's so few half spaces, let's say if the genus is high enough, there's only the upper and the lower one, then you need to be close to always the same half space. So you can't change from, say, upper half space to lower half space. But what does our sweep out do? So this part in this upper ball is connected through these holes that you see well in the back with this lower half space outside the ball, outside the sphere. Okay? And the lower part inside the sphere is connected through these holes to the upper part outside. So if the sphere is shrinking, then this upper half is disappearing and only the lower half space survives. But if the sphere is expanding, then there's less and less of this lower half space and more in this upper semi-ball. And in the limit, we only have the upper half space. So actually, if we fix one region that is bounded by this shrinker along this sweep out, then that moves from the upper half space to the lower half space. Okay? So that means at some point, that region has to be far from a half space, and therefore the Gaussian area needs to go above this threshold in the Gaussian isoperimetric inequality stability result. Okay? So that's how we obtain the mountain pass condition. Now we use this black box and say now there exists a min-max sequence, so some objects that are converging in a very weak sense, so in the sense of varifolds, to a smooth embedded minimal surface in this Gaussian space. And minimal surfaces in Gaussian space are the self-shrinkers. Okay? And we already have this symmetry. This is preserved in this min-max procedure. And for this we use this equivariant min-max theory of Ketover and Su. Good. Now, what is the problem? Why have we not fully finished our proof yet? Well, because we have only this varifold convergence. And this varifold convergence is very weak. And it's in particular too weak to control the topology of the limit. And all kinds of things could go wrong in varifold convergence. Okay? So although this sigma g arises limit of smooth surfaces that all have genus G, it could happen that topology is gained or lost in the limit. Okay? So it changes. And so to finish the proof of theorem 1, we need to control the genus. We said already we can't control the ends. That's another thing, another artifact of this weak convergence in this min-max construction. But at least the genus we can control. So how do we do this? Okay, so let's now only look at the cyclic subgroup of the dihedral group. So that's the group of rotations around the vertical axis. And remember that if we take two rotations around the horizontal axis of 180 degrees, then we get a rotation around the vertical axis. Okay? So this is subgroup of order g plus 1. There's, the rotation is of angle 2 pi divided by g plus 1. And the vertical axis we call psi 0. Okay? So here is a lemma. Given any g, any natural number g, and some sigma that is closed, connected, embedded, and has this cyclic symmetry group, and it also has genus gamma between 1 and g. Okay? Then there's two options. So if this sigma is disjoint from the vertical axis, then it must have genus 1. So it's, for example, a torus, could be Angenen's torus around the vertical axis, doesn't intersect it. Otherwise, if it does intersect the vertical axis, then the number of these intersections is 4 and the genus is G. Okay? And the other example is actually again Angenen's torus, but this time you put it vertically so that it's sort of spiked up on this vertical axis, and it has 4 intersections, and that's another option of doing it. Okay? Good. So a direct corollary from this, or almost direct corollary, is that if we now have some compact connected dihedral group equivariant surface of genus between 1 and g, which is properly embedded in some ball, then either you have that there's no intersections with the vertical axis, or if there are some intersections with the vertical axis, then the genus is exactly G. Okay? And this corollary follows from the lemma by just closing up the boundary components. Okay? So now here we have these objects which are properly embedded in a ball, so they might have boundary in the ball, and what we can do is we can just close up each boundary component with a disk, and we can do that in such a way that the disks don't intersect. Okay? And then we use the lemma. Good, so how do we prove this lemma? So any intersection of our, in the lemma, closed, so remember we have a closed, connected, embedded cyclic group equivariant surface, so every intersection with the vertical axis must be orthogonal because of the cyclic symmetry. And the number of these intersections is well defined, and it's finite and even, okay? Even just because this closed object has an interior and an exterior, and so therefore it's clear that every intersection must come in even numbers, okay? Now, this means that the number of intersections is some 2j for some non-negative integer j. Okay. Then what we do is we look at the quotient of our surface by this cyclic symmetry group, which is an orientable surface, this boundary, and it has therefore some Euler characteristic. Let's call the Euler characteristic just 2 minus 2 gamma dash, where gamma dash is the genus of this newly constructed object. Okay, then we have the Riemann-Hurwitz formula. So just think of how do we get sigma back from sigma prime. So we just need to add this sigma prime g plus 1 times. But then the thing is, the points that are actually on the vertical axis, we don't need to add them again. So if we compute the Euler characteristic via the formula of vertices, edges, and faces, then we notice that these points need to be subtracted again. Okay, so we get the Euler characteristic of our sigma is g plus 1 times the Euler characteristic of this quotient, minus these points that lie on the vertical axis that we don't need to add another time. Okay? So, plugging in Euler characteristic being 2 minus 2 gamma or 2 minus 2 gamma dash, we get this identity here. Okay, that's just the same formula now with Euler characteristic rewritten. Okay? Now let's look at how can we satisfy this. So if sigma is disjoint from this vertical axis, then the number of intersections is 0. So j is 0, and then we just get minus g here. And the assumption that our gamma lies between 1 and g implies that gamma prime must be 1 and gamma must be 1. Okay, it's the only way to solve this. If instead j is equal to 1, that means this term here cancels, then we just have gamma is equal to g plus 1 times gamma prime. Okay, but now gamma lies between 1 and g, so gamma prime cannot be any positive or any non-negative integer that would contradict the fact that gamma lies between 1 and g. And therefore, we can't solve this. If j is bigger or equal to 3, then we have a similar thing happening. Then here we have at least 2g, okay? And then again, the fact that gamma lies between 1 and g, we cannot solve this, okay? So therefore, the only remaining case where this is actually solvable is that j is equal to 2, so that means the number of intersections is 2j, so equal to 4. And in that case, what do we have here? We have G here and gamma that lies between 1 and G. So gamma must be G and this gamma prime must be 0. Okay, it's the only way that you can solve this. So therefore we get this lemma and the corollary, and now we apply this to the self-shrinkers that we have constructed. Okay, so now if the genus is 0, then we know that we have the horizontal plane. Why? Because there's only 3 genus 0 self-shrinkers. There's a plane, the sphere, and the cylinder, but we do contain this symmetry axis. So we do contain this horizontal axis, and therefore it must be the plane. But then the min-max theory tells us that the Gaussian area is equal to the width, which we have proven is bigger than 1 plus delta for some positive delta. So the width is strictly bigger than 1, so therefore that can't happen. And so we know that the genus of our limit is at least 1. Okay? And then by a general lifting argument that always works, so that uses ideas of Simon's lifting lemma, the genus can actually go down, but it cannot go up. So the genus of our self-shrinker in the limit is bounded by the genus of the approximating sequence, which is always G for every element in this approximating sequence, in this min-max sequence. Okay, so that's a result that can be found, for example, in works of Lee or Delellis Pelandrini. Okay, so now we already know that our limit has genus between 1 and G, so that's what we want, so that we can apply the lemma. Okay, now the problem is the lemma and the corollary. The lemma is for closed objects, and the corollary is for objects inside a ball, but now we have a non-compact object. But by Louvain's result, we know that there exists a ball around the origin, such that every connected component outside the ball is diffeomorphic to either it's either a conical end or a cylindrical end, so it's some cylinder or half cylinder topologically. Okay, and then we can use this to actually deduce that the genus must all happen inside this ball B. Okay. And now we can apply the corollary, because the boundaries inside this ball, where we have these ends, they can be closed up with topological disks. Okay, so that means the lemma or corollary tells us we have now genus between 1 and G, we have the dihedral symmetry, and we're in the situation where we can apply this because we're inside a ball, so therefore the genus must actually be equal to G. And that shows that our self-shrinker has actually not lost genus in this weak varifold convergence, but it's actually a self-shrinker of genus G. Okay, let's say something about the proof of theorem 2. Okay. So first, remember we let the genus become larger and larger, but we have this uniform bound on the Gaussian area. That works independently of the genus G. That's just a bound that comes from the fact that our model sweep out has Gaussian area bounded by the area of the plane and the sphere. Okay, and the largest sphere is the one of radius 2 with area 4 over E. Okay, now by Allard's compactness theorem, if you have this area bound, then you can pass again in a very weak sense to a limit. And the limit is a stationary integer varifold, and so that's in a certain sense a minimal surface in Gaussian space, so a self-shrinker, but it might not be smooth. Okay, and in our case it's the intersection of two smooth self-shrinkers, the sphere and the plane, but it has an actual intersecting circle, so it is actually not smooth. Okay. Now, what we also know is that we contain these horizontal axes, and we contain more and more of them because there's more and more symmetry if the genus becomes larger. And in the limit, we must actually contain the entire horizontal plane. So whatever we get as a limit is always the plane plus something else. Okay. And then what we do is we define gamma to be the set where the second fundamental form blows up. So whenever the second fundamental form remains bounded, then the convergence can actually be improved easily to smooth convergence. And by blowing up, I actually mean in some integral local sense. But let's not go too much into details. When you have bounded second fundamental form, then that easily gives you smooth convergence. So this is the set where second fundamental form is not bounded, and therefore the convergence is bad. Okay? And as I said already, away from this gamma, the convergence is locally smooth. And we will now need to analyze this set gamma where the convergence is bad. Okay, so the first step is that the genus restricted to any neighborhood of a point in gamma is unbounded as g goes to infinity. So this is obtained by a localized Gauss-Bonnet estimate. So the fact is, you know that you have second fundamental form in some integral sense. So say second fundamental form square integrated over a small ball, and you make the size of the ball smaller and smaller. That is very large. Then by a Gauss-Bonnet argument, the genus inside that ball must also be very large. Okay. Next, we know that this set also has rotational symmetry because our limit object, in particular, we always have this cyclic symmetry group, and if the genus becomes larger and larger, there's more and more rotations, and in the limit, everything is fully symmetric under any rotation of any angle. Okay. So our bad set is rotationally symmetric, and it consists of a bunch of circles. Okay, and in fact there is at most one circle, and this circle lies in the horizontal plane, and that's done by the previous lemma. Okay, which shows the following. So if you have a circle, then if you have one singular point, then the rotational symmetry says you have a whole circle, and then what you could do is you could take a little neighborhood of this circle, and the previous result says that the entire genus already must lie in that region, because the genus will be between 1 and the total genus, and the previous result says it's actually concentrated already in that tubular neighborhood around the circle. Okay, so therefore there can only be one circle, and then because dihedral symmetry tells us that if it's not lying in the plane but say above the plane, then by symmetry there must also be one below the plane. So the symmetry gives us that this circle lies inside the plane, and there is at most one. Okay, good. What now we get next is we could have also a point at the origin, which is bad, or we could only have the origin, which is a bad point. Okay, so let's quickly discuss a case where only the origin is a bad point. Then So shrinkers are nice objects. If there's only one singular point, then it's a removable singularity. So the limit actually, which contains the plane, can be smoothed and is actually, in fact, simply the plane. Okay, and it could be the plane with higher multiplicity, so it could converge. So imagine, for example, if the sphere somehow becomes flatter and flatter and moves out, you could possibly think you might have a multiplicity 3 plane or something like that. In that case, actually, the origin wouldn't be a point of bad convergence, but let's just assume you could have something like that. But then the problem is that we know that our Gaussian area is less than 3, and therefore we can actually not get the plane with multiplicity 3. And again, dihedral symmetry says that multiplicity must be odd. So any odd number, positive odd number less than 3 must be 1. Okay, but that would actually mean that our limit is again simply the plane, but that's what we have already discussed, so we can't have a plane. And in fact, we use this gap result of Bracke, which says if the limit is a plane, then there's a gap, so the next close, you cannot have a self-shrinker which has Gaussian area very close to the plane, but isn't the plane, but our approximating sequence would have Gaussian area closer and closer to the one of the plane. So that gives you a contradiction. Okay, so again, the plane can be ruled out, similar as we have already ruled it out earlier. Okay, good. Now, what we get last is that actually we have now one circle where the convergence is bad, and that circle has a definite radius, and then the intersection must actually be the intersection of the plane and the sphere. Okay, and let me quickly say something about how we prove that. So imagine first that at this circle, possibly lots of surfaces could meet. Okay, so then we could take again a little tubular neighborhood around that circle, and by a result similar to our structural lemma, we would actually know that in this tubular neighborhood we actually have exactly 4 boundary components. Okay, and that means that actually 2 are created already by the plane, so you can only have one going up and one going down. So you cannot have more than 2 smooth surfaces intersecting. And remember that away from this circle they're smooth. Okay. So then next, because we have a stationary varifold, there's a balancing condition. So actually the piece that goes up and the piece that go down, they need to intersect this circle at a 90-degree angle. Okay, so what you could do now is forget about the plane and put back in the circle, and then you get a smooth self-shrinker. Okay, so we know already that our object is the intersection of the plane and one other smooth self-shrinker that also intersects this circle. Okay, and next we also know that it has genus 0, because the entire genus was already captured in a neighborhood of this circle. So that self-shrinker itself must have genus 0, but genus 0 we only have the plane, and we can't have the plane, otherwise we would be in the case of high multiplicity planes, which we have ruled out. Or it's a sphere, that's what we want to show, or it's a cylinder. Okay, now why can we rule out the cylinder? The cylinder can be ruled out because of that slide that I showed you very early, which says the plane plus the sphere, which is our upper bound for how much Gaussian area we have, is strictly less than plane plus cylinder, because the cylinder has strictly larger Gaussian area than the sphere. Okay, so it can't be in the case where our limit is an intersection of the cylinder and the sphere and the plane. So it must be the sphere and the plane. And then we're done with theorem 2. So now let me say a little bit something about open problems. So we actually conjecture that one could also try to do some desingularization of a cone or of a, we start with a cylinder, and if you do a min-max or a desingularization approach, it will probably open up to be conical ends. So you should be able to obtain these self-shrinkers that have two asymptotically conical ends and odd genus. Okay, and this should be a similar result to the one with sphere and plane intersected and desingularized, or should possibly also work with a min-max approach. Now the problem with the min-max approach is that you would probably need to use two parameters, and again you have this very delicate issue of controlling the ends. Okay, and here the conjecture would be that these surfaces converge locally to the union of the cylinder and the sphere as genus goes to infinity. Okay, now let me say why is a min-max approach to this very difficult. Okay, so here we have this object. Now if you would close up this cylinder here, then you would actually get topologically exactly this. So you would on the one hand change the genus, and on the other hand change the number of ends. So now the problem is that a min-max construction, so if you for example try to construct this by a two-parameter min-max, there's no way that we can prevent this Angenen torus to just open up and create this conical end, and at the same time there's no way, if you try to construct these with a min-max construction, that these ends don't just collapse and you get actually this. Okay, this is the same picture but with higher genus. So this is the genus 48, Angenen torus intersected with sphere, and this is genus 47, cylinder intersected with sphere. Okay, and again the number of ends is different, the number of the genus is different, but they probably might arise from a similar min-max construction, or if you try to do a min-max sweep out, you have no control over which of the two objects you get, and you might get even a completely different one. Okay, so therefore this is why I said controlling both genus and ends is in general a very difficult issue, and in this case it's unclear how one would resolve this. Okay, let me also mention another problem. So if you try to do this via desingularization, so the question is, would it be also possible to desingularize the plane and the cylinder? Okay, so we know that the sphere and the plane works, and we have sphere and torus which works, and now sphere and cylinder, that's our conjecture that this also works. And it seems that actually this works best at the level, so the Shirk surface of desingularization should be at the level of the sphere. Then numerically it works best. But now the question is, could you also do this with a plane and a cylinder? If yes, then Ilmanen's conjecture that anything with a asymptotically cylindrical end must be the cylinder would be incorrect. But it's unclear whether this is possible. Okay, and our numerics actually suggest that it might not be possible to do that. Okay, and with this I have ended, so I hope you have enjoyed the talk, and I hope you enjoy this whole event.